There's a story. It goes like this. Down on the beach, there's a store. It sells two things. It sells ice cream and sunscreen. And as the days go on, they track the sunscreen and the ice cream sales. The day that they sell one bottle of sunscreen, they notice that they sell one ice cream cone. Days that they sell no sunscreen, they notice that they sell no ice cream. Then one day comes and they sell 3 bottles of sunscreen. On that day, they sell 9 ice cream cones. On a day, and then the next day, they come in and they sell 4 sunscreen bottles and they sell 16 ice cream cones. The day after that, they come in, they sell 2 bottles of sunscreen and 4 ice cream cones. And so what we tend to do in mathematics is we go find the relationship. And so a person will say, oh, well, if I take my sunscreen and square it, that's equal to my ice cream, right? And the problem with doing that is it works. 1 squared is 1, 0 squared is 0, 3 squared is 9, 4 squared is 16, 2 squared is 4. The problem is it works, and we're so okay with these things not making sense, right? That doesn't actually make sense. Because sunscreen and ice cream are not directly related. I don't go into Walmart and think to myself, oh, I got to buy sunscreen. Well, I got to buy ice cream too. And so what parametric relationships do is they seek to put data together in meaningful ways. This works, but it's actually not meaningful because there's a third variable that we have to consider. What if I gave you this? And I told you that along with sunscreen and ice cream, we also track the temperature, okay? So on the first day, the temperature was 68 degrees. On the second day, it was 71 degrees. The third day, it was 65 degrees. Fourth day, it was 73. The fifth day, it was 74. The last day, it was 72. What do you notice now? We'll take a look at this. You have 2 pieces of data that have zeros and then 68 and 65. As the temperature crept slightly above 70 to 71, you sold 1 bottle of sunscreen, 1 ice cream cone. But as it got warmer, 73, you sold 3 and 9 ice creams. It became 74, you sold 4 bottles of sunscreen, 16 ice cream cones, and it was 72, and there were 2 and there were 4. And so in this case, yes, ice cream does equal sunscreen squared. And the square root of ice cream is equal to sunscreen. But there's a variable here that really goes untouched unless we know what to look for. Because really, sunscreen equals the temperature minus 70. And ice cream is equal to the temp minus 70 squared. Okay, maybe this is a silly example. But when we put some parameters on it, the temperature has to be greater than or equal to 70. This actually makes a lot more sense than talking about sunscreen and ice cream. It doesn't make sense. Ice cream and sunscreen aren't necessarily related. I don't walk into a store and think, oh, I bought a certain amount of sunscreen, therefore I must buy ice cream. Really what I'm thinking is, what's the temperature outside? If it's above 70, I might go to the beach, I'm going to buy some sunscreen, but also it's hot, I'm going to buy some ice cream. These are more meaningful ways to define functions, is looking for a third-party variable that's going to help us out. And so parametrically defined functions is another natural way to define functions. More generally, relations is to define both elements in the ordered pair xy in terms of another variable t called a parameter. This is what it looks like. They might say this: my x coordinate is equal to t minus 1, my y coordinate is equal to t squared plus 2, so find the points determined by t equals -3, -2, -1, 0, 1, 2, 3. Well, this is what it looks like. If I take t minus 1, that's -3 minus 1, so this would be -4. T squared plus 2 would be 9 plus 2 would be 11, and so my ordered pair would be -4, 11. Okay? And so when you do parametric functions, you're taking 2 variables that are defined by some other variable t. So I defined sunscreen and ice cream by temperature, which actually made more sense because I'm looking at things that are related to temperature, not necessarily related to one another. Okay? So x is not necessarily -2 times 4 plus 3. They're both based on t. And so as I go down the list here and I square these things, this is going to be 6, and so my ordered pairs are defined this way. So -1 minus 1 would be -2. negative 1 squared plus 2 would be 3. So I've got negative 2 comma 3. And here I've got, this would be negative 1. And then this would be 2. So I've got negative 1, 2. For 1 it would be 0. And then 1 squared plus 2 would be 3. So I've got 0, 3. Here it would be, so I see the pattern, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 11, 6, 3. So minus 5, minus 3, minus 1. Okay, I gotta keep doing this one. So if t is 2, then t squared plus 2 would give me 6. And then t squared plus 2 would be 11. So I've got 1, 6, and 2, 11. So to define things parametrically is to say, okay, I've got these t's, and I'm defining them x, y, together x and y make a pair. But why would I want to do this? Okay, why would I want to look at these variables in terms of a third-party variable? Well, with the sunscreen ice cream example, they're not really related to one another, but they are related to temperature. Okay, so sunscreen and ice cream have nothing to do with one another, but when the temperature gets hotter, people buy more sunscreen and they buy more ice cream. Okay, and so if I look at what this actually means, check this out. If I look at y being t squared plus 2, and x is equal to t minus 1, this means that t is equal to x plus 1. Well, what can I do here then? Check this out. If I can define what t is, this is like solving systems of equations. I can plug it back in. And so y is actually equal to x plus 1 squared, because that's what t was, plus 2. And so y is actually equal to x squared plus 2x plus 1 plus 2 is equal to x squared plus 2x plus 3. Notice what I just did there. This now becomes like what we did in section 1.4. It becomes a composition of functions. So t is a function. The function goes into the other function. So when a function is inside a function, it's composed. Okay? And so what we're doing here is we're building functions from functions and finding relationships that are actually meaningful. What we do with that is we find inverse relations. So I want to be able to work backwards and say, okay, I sold this much sunscreen. What did that mean the temperature was? That helps me draw conclusions. So the ordered pair AB is a relation if and only if the ordered pair BA is in the inverse relation. Okay? And so when I switch x and y, it allows me to use something called the horizontal line test. Let's look at a graph. If I have a graph here, whoa, that's crooked. If I have a graph here, still crooked, man, I'm struggling right now. And it's going to be the squaring function, and I'm going to look at it and I want to show you guys exactly how this works. So let's say I've got a graph that looks like this. And I look at this and I ask, is it a function? Well, check it out. Vertical line test means y equals x squared is a function. Okay? Vertical line test says touches at one point, it's a vertical line test. Okay? The inverse, meaning the horizontal line test, tells me the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation at least at most one point. So horizontal line test the inverse is not a function. Okay? And so I can't look at x squared and say, okay, the inverse is a function. Well, let's look at what that would actually mean. So if y is equal to x squared, to find an inverse, we're going to talk about this in just a minute, I switch x and y, so x is equal to y squared, and then I solve for y. So I take the square root of both sides. Well, then y would be equal to plus or minus x. Okay, plus or minus the square root of x. Well, why isn't that a function? Well, if I look at plus or minus the square root of x, check this out. The positive square root of x would look like this, the negative square root of x would be like this. And so now it doesn't pass the vertical line test. So this right here is the inverse. The inverse is not a function because it doesn't pass the vertical line test. Well, an easy way to shortcut that is to say, let's test it horizontally in the original and see if it's a function. If f is a one-to-one function with domain D and range R, the inverse of f, denoted f minus 1, so inverse, is the function with domain R and range D defined by f of negative 1 is b and a, f of negative 1 of b is equal to a, if and only if f of a is equal to b. Okay, well, what does this mean? It means that if I have the domain and I stick it in and I get a range R, for the inverse, if it's one-to-one, I can switch them. So in the inverse, if I put in the range into the inverse, I should get all of the domain. Well, you're like, Mr. Seris, I don't really understand this. Let's look at an example and see how this works. Okay, and so if I look at the x cubed function, check this out, and I draw the x cubed function, that ain't bad. I know that this is a function, right? Passes the vertical line test. Is a function. Okay? Well, if I do the horizontal line test, so f of x up here was equal to x cubed, right? So this means that f inverse of x, so the inverse is a function. Because f of x and f inverse of x are functions, meaning it passes the vertical and horizontal line test, then f of x is 1 to 1. It's called a one-to-one function, meaning everything in the domain maps to the range, and everything in the range maps back to the domain in the inverse. So here we go. If I'm going to find the f of inverse, if f of x is equal to this, my first thing is to switch x and y. And number 2, solve for y. So here we go. If I switch x and y, I'm going to have, so for y equals 2x over x minus 1. That would mean that I have x is equal to 2y over y minus 1. So I make the x's y's and the y's x's. So when I solve for y, I've got x is equal to 2y over y minus 1. So I'm going to multiply by y minus 1 on both sides. X times y minus 1 is equal to 2y. And so what I'll do is I will distribute that. So xy minus x is equal to 2y. And then I'll subtract 2y. And that will give me xy minus 2y minus x equals 0. And I'll add x. Remember, I'm trying to get x on one side and y on the other. So xy minus 2y equals x. And then I'm going to factor out a y. So y times x minus 2 is equal to x. And then I'll divide by x minus 2. So y equals x over x minus 2. And so that means that f inverse of x is equal to x over x minus 2. Okay? So how do I know if I'm right? This is the really cool part about this. Okay? I know if I'm right because they will be reflections across the line y equal x. So if I graph f of x and f inverse of x, they should be reflections. So let's say I graph 2x over x minus 1. I'm going to go here. So I'm going to have 2x divided by x minus 1. And then I'm going to graph, what was my other one? Let's see here. X minus 2. Check it out. Okay. if I graph the line y equals x, check this action out here. Put the keyboard away. Put this away. Watch this. They're reflections of one another, right? So the point of inflection is right on the line, y equals x. They're reflections of one another. This is awesome. So I know that I'm right. And so there's two ways that we can do this. So they're reflections of one another, or if I compose them together. So if I do f of g of x, then I'm going to get x. So they're going to cancel. Everything's going to cancel out. I'm going to have x. If I put f of x into g of x, so I do f of g of x, or g of f of x, I should get x. And so what does that mean? Well, that means that if I do f of g of x, or in this case, f of f inverse of x, it should equal x. Let's just do it. So 2x over x minus 1. This is f of x. And f inverse of x is equal to x over x minus 2. If I compose those, let's see what happens. Here we go. It's going to get a little crazy here, but let's just try it. Okay, so this is inverse composition rule. So I'm going to go f of f inverse of x is equal to 2 times x over x minus 2 over x minus 2 minus 1. Well, that's just silly. Let me write it again. 2 times x over x minus 2 over x minus 2 minus 1. You're probably like, what in the world is going on here? Well, let's just stick with it. 2x, so I'm distributing this in, over x minus 2 over, and so if I've got x over x minus 2 minus 1, right? That would be x minus 2 over x minus 2, right? So common denominator on the bottom, stick with it. Stick with it. Have some perseverance. So on top, I've got 2x over x minus 2. And on bottom, I've got x minus x plus 2 over x minus 2 equals 2x over x minus 2 over x minus x. Oh, look at this. Look at this. X minus x is 0, so 2 over x minus 2. Dividing by a fraction is the same as multiplying by the reciprocal, right? So 2x over x minus 2 times x minus 2 over 2. So these cancel. And the 2's cancel. So I get that it's equal to x. Well, what does that mean? That means that when I put my inverse into my original function, everything canceled out and I got x. That proves that they are inverses of one another. Also, I graphed them. They're reflections over the line y equal x. That proves that they're right. So if you're stuck on a test, you're like, I don't know if I did this right. Test it. Put it in. Did you get x? Then it works. Graph it. If it is a reflection over y equals x, then it works. Okay? Here's another one. Show algebraically that the function f of x equal to x cubed plus 2 and g of x, cube root of x minus 2, are inverse functions. So here's what I'm going to do. I'm going to do f of g of x. So I'm going to put g of x into f of x. So x cubed plus 2. Instead of x cubed, I'm actually going to do the cube root of x minus 2 cubed plus 2. Well, cubed and cube root cancel out, so I've got x minus 2 plus 2 equals x, so they work. You could also do g of f of x. So if I take the cube root of x minus 2 and I don't put that in, I put in x cubed plus 2, it's going to be the cube root of x cubed plus 2 minus 2 is equal to the cube root of x cubed, which is equal to x. So they work. F of g of x works, g of f of x works, so therefore g and f of x and g of x are inverse functions of one another. Okay, guys? That's the basics of it. That's how it works. Thanks for watching, and we'll see you next time.